Hey Aaron, how are you?
Very much thank you.
Yeah, it's good. Hi Evan, nice seeing you. So we are waiting for Fatima and eventually David. Um, so I did send the links mm, by the email and as in the common chat. So the goal of the meeting is to practice collective editing, although um, because of the changes in the style, we are going a little bit away from coherent arrangement, but still there is a hope to submit several manuscripts by the end of semester. So there are updates that tomorrow is the uh, postponed deadline for Pacific Chem conference. Please consider to submit there whatever your Sunnybell abstract, or if you have something better. There is a chance that by the time of the conference there could appear some funds to have this travel, and if it will not happen, some of the group members will be able to represent the group, and it will be one more presentations or posters in your um, list of conferences. So it is a good thing. Oh, hello, Fatima. I see you have joined. So I believe Fatima has submitted the abstract to Pacificum, right?
Yeah.
Yeah, very good, very good. So there is a chance that there will be funds for travel, and it is at the end of December. Um, Also, since recent changes in pandemic, some people feel scared and not submitting abstracts, so chances to get oral presentation are a little higher if you decide to do so. Um, Today we will practice collective editing of the materials, and maybe half an hour before completion of the meeting we will go over edited materials and share the outcome of editing this, suggest to authors. Um, Next week, Wednesday 22nd, Kevin will do his master thesis defense, and I think it will be reasonable if we ask him to practice the defense on the group meeting on Tuesday, just a day before the presentation. So I'll I'll chat with Kevin how enthusiastic he is about this presentation, and if there will be more time, we can go over um, a little bit of materials for the manuscripts. If not, Kevin will be helping to Kevin will be main goal of the next meeting, and then it will be very close to submissions in 2 weeks. So I think it's time to um, have the conclusions and introductions to the papers. Um, there are we will start doing it very soon. Mm, there are also a couple of thesis defenses on next on coming Thursday and Friday. So it is master thesis defense in physics by Braden Wade and Nathan Walker. So try to share links if anyone wants to join and listen to them. It could be interesting. So Braden will defend a thesis on modified carbon nanotubes, on the covalent bonding to nanotube, and Nathan will do a thesis on electron transfer on the interface between metal and semiconductor. So it's of course optional and not mandatory, but if your schedule is not busy and you want some scientific entertainment, this would be great. Before we go to the editing activity, I suggest Aaron will explain some interesting molecular dynamics trajectory related to his research. Aaron, do you support this idea?
Sure.
Okay, then I will place the movie on the screen for everyone, and you tell the story. What should we focus on and how to analyze it, and then maybe there will be either questions or suggestions. Okay, it is playing. It is playing now.
So a quick takeaway is that the ligands, when they're near the surface, they have opposite charges. So the carboxylate, which has the red atoms, is negative, and the ammonium, which has the blue atoms, is positive. And so when the negative carboxylate desorbs from the surface, it kind of attracts the ammonium and it steals one of the protons from the ammonia. So it's an example of surface chemistry happening on the surface of this nanomaterial.
Mm-hmm. So what is the maybe before we go to discussion, can you remind for everyone what is the system? Although we all were reading your manuscript drafts, just briefly, what is on the picture? Like, what is the color code?
So it is a quantum dot, and all of its surfaces are exposed. So each side of the cube has oppositely charged ligands coordinated to the surface.
Mm-hmm.
So it's an inorganic core, and then it's surrounded by charged surfactant.
Okay.
And experimentally, like, it's known that these surfaces are relatively unstable. So when people do, I don't know, some sort of NMR experiment, they see that this type of chemical reaction happens very readily. So it's generally in like a dynamic equilibrium, where these two pairs of ligands will, so this reaction goes back and forth.
Mm-hmm. So this highlighted carboxylic groups, where they were bound before the reaction starts.
So carboxylates were chemically bonded to surface lead atoms,
And
and the ammonium are just coordinated to surface bromine.
mhm. So the lead ion to which these carboxylic groups were bound, um, is it on the surface, on the edge, or on the corner? I'm trying to show it by mouse, but I'm not sure if sharing screen will show my mouse.
I guess it'd be called an edge atom.
Uh-huh. So how many coordinating bromines will have this lead after both of this carboxylic group desorbs? Total four. Okay, okay. So it is 4 coordinated, and this carboxylic compensated to 6 coordinated.
Yes.
Does this desorption occur in the electronic ground state?
From what I can tell, yeah.
How? But what are you showing here? Is it ground state or excited state?
So this one is excited state.
Mm-hmm. Is it room temperature?
Yes.
Okay. Um, is it possible to dynamically demonstrate the distance from the host lead ion to these two carboxylic oxygens?
I'm sure it's possible. I couldn't figure out how to do it with the VMD.
Yeah. Please try and consult Yulun if he agrees to help, because it is. He was doing it in the past, and I did it a couple of times in the past too. If I can remember, it should be quite simple. Like add label, and among the list of labels there is a distance, and you click on pair of atoms, and then the distance is displayed at each time step of the trajectory. Another question: how soon this desorption will happen? Can one measure the time interval before from starting of the trajectory to the instant of time when distance from lead to oxygen becomes bigger than a threshold, like maybe bigger than 3 angstrom or bigger than 4 angstrom?
I guess in my figures document,
Uh-huh.
I have the 2D oxygens plotted versus time.
Mm-hmm.
So I guess the thing with this simulation is that if you look at time 0,
Mm-hmm.
just from doing the geometry optimization, one of the ligands was already in a, I guess, a state favorable
Mm-hmm.
to desorb. So just from this dynamics, it's set up favorably for this type of reaction to happen.
Okay. I'm trying to set up an arrangement of experiment where desorption will happen sooner for excited state and later if the electronic configuration is in ground state. To prove right or wrong that excited state potential surface is more supportive for desorption of the ligands.
Mm-hmm.
So you believe it is possible to prove?
I mean, I could just use the same starting point, the ground state photonic structure,
Mm-hmm.
and then I think I already have some of that started. I just haven't run it for a comparable amount of time yet.
Okay, okay, very good, very good. Yeah,
So it should be possible to look at the comparison.
I see, I see. Other specific questions from? Does anyone want to ask Aaron more questions about this trajectory? If it is not the case, I invite everyone to start editing activity. We do have 3 documents. The whole draft of a master thesis or draft of a paper from Kevin, the method section from Fatima, and results discussion and the concluding part from Yulun. So I will start editing. We may mute the microphones and let's plan on getting back to each other at 5:30 for sharing comments on the editing. Uh, does this plan sounds reasonable? Okay, then I'm muting microphone and starting editing. If anyone needs to chat, just unmute the microphone and express whatever needs to be done. Whew. Hello again. Are we close to completion of the comments? Okay. Um, I have seen that Aaron has practiced accessing the, and Fatima has practiced editing the document in Google Docs, and I think they both were editing the work of Kevin. So it is what I see in my email. So I believe that Kevin may want to go onto the link and access the the file and see what has been added, which edits have been practiced for his online shared version. So it is what I see in this online version, and there are some comments and suggestions, and we may use of this format in the future. So just bringing to attention of Kevin's that the comments are recorded, and one doesn't need to send files for this set of comments. One just needs to open them in Google Docs or download it from there. So I suggest we will go in the order from the work of Yulun to Fatima and then to Kevin, and let me check if who wants to provide comments to Yulun's work. Aaron, are you? Did you glance through? Do you have some suggestions or comments?
I read it, but I didn't really see anything outstanding or anything to comment on.
Huh. Okay. Thank you. Kevin, would you like to give some comments to Yulun's work? Fatima, do you have something to share? I can bring it to the screen and you can just tell where to focus.
Yeah, I saw it, but I don't have any suggestion.
Okay, then I'll share my comments and then we'll go forward to the next next work. Double check. Okay. So for the concluding section, I do not have any complaints. It is written great, but one may help reader to understand the logic, to focus, like that system without electric field is used as reference. It is unperturbed. Then one may, I know that earlier it is mentioned that there is a specific range where field was changed, but one can just highlight that there is a certain range selected. It is kind of done. Strength rather than intensity. Measure measure of charge. Okay, it doesn't change any logic of narration, but one may highlight that the strengths of this work, there is a technological and industrial strengths, and there is a intellectual strengths. And intellectually, the system is experiencing perturbation of two types of perturbation simultaneously. One perturbation that it is external electric field that affects the offsets and of orbitals and their shapes, and another perturbation is non-adiabatic interaction with phonons that induces transition. And in some sense, these two perturbations are competing. They are either helping or mixing each other. And generally, it is interesting challenge, and partial or complete address of this challenge is interesting. Also, the conclusions show everything, but it doesn't. Well, for me, it is very academic. I would like maybe one can make it a little bit more personal, a little bit more emotional. Like what select out of all these useful findings, which one was most surprising or most impressive, just to help reader to navigate through. And for the figures, I do see arrows in figure 1, and they were not defined, or maybe I missed their definition. Figure 2 is great. For the figure 3 and 4, the dipole, which is changing versus time, and the rate of change of this dipole is currently analyzed and presented in the figure 4b. But in addition to the rate of relaxation, there is another feature that may or may not be different. So the absolute value of this dipole at time equals infinity at the end of trajectory may depend on the field strength and on excitation energy. And if there is no dependence, one can just verbally address it. If there is some dependence, maybe it can be beneficial to record it either as a table or as a figure. Why this question is being asked? What is the value of this question? If the extreme values of electric field swap the order of HOMO and LUMO, it may disable charge transfer or swap the direction of charge transfer. Hypothetically, it is possible, and we may want to assure reviewer that it doesn't happen, or if it does happen, we can tell that like if the electric field stays within certain range, maybe if electric field converted into voltage units is below the original gap, then nothing dramatic is changing, and the dipole at infinite time stays the same. If one applies larger electric field, then some dramatic changes are happening. And for industrial applications, it is reasonable to focus on the regimes of operation when everything goes continuously and without big effects. But as for fundamental research, it will be it will just attract curiosity of reviewers, and they may ask it even if we do not mention it. Like, what are the limits of applicability? Can we believe that this final measure of charge separation will be the same for any electric field, or there are some limits? Okay, I'm done. Does anyone has more questions on this work? If no, let me suggest we move to the work by Fatima. Do you have some suggestions or criticism for Fatima's work? Okay, Aaron, do you have some observations to share?
I looked through, but didn't see anything that I wanted to comment on.
Okay, Kevin, do you have any comments to Fatima's work that you want to verbally, that you want to focus attention verbally? If you don't, you can just send your comments electronically at the end of the meeting. So then let me just briefly go over all my comments because I have some of them are just edits, but Hamiltonian, this here, it doesn't look general. It is Hamiltonian only if we are looking on a specific band, either HOMO or LUMO. And generally, one may want to generalize this equation for multiple bands. In everything after that, there are no simultaneous electrons and holes. It's only one particle, and we may mention it as an approximation. Also, I do see that there is a similar equation, like time-independent Schrödinger equation, is repeated again and again in several forms. I do not mind, but please read through once again and inspect if one can minimize the redundancy. Please double check if this angular momentum operators need Planck constant or imaginary unit. I hope not, but it's better to double check. And since this operator is used in what follows, one may mention if the derivatives are implemented as finite differences, like explain what this how the finite differences are implemented numerically, because reviewer will likely ask it anyway. Then so I do see time-independent Schrödinger equation 3 times. Equation 14, equation 15, and the next equation. And I do not see big difference in them, rather than in one of the versions there is a explicitly mentioned projection on z-axis. So just double check if it is really needed. Then there is a transition from time independent to time dependent Schrödinger equation. So one may give a little heads up when it is needed, like if one goes beyond stationary states. It's kind of known and trivial thing, but we may want to help reader and reviewer to read the whole document at once without any stops, so that each step sounds logical. Evolution operator. Then we may mention that the initial condition that is being used for time dependent, for time dynamics, is a selection of humans. We intentionally designed this initial condition. If we have in mind we can mention, if it models some physical situation like excitation with optical field, or how one brings the system from ground state to one of these Gaussian states. If no, one can tell just that it is a mathematical tool to explore a system, but a reviewer will try to ask questions like this, and I know that some of them bring us away from the zone of comfort, but we better think about it ahead. Values of initial momentum and initial position. And after this initial conditions, one may give additional comments on observables. Since you are already using trajectories with expectation values of kx and ky as function of time, one may mention it after, so that initial condition and time dependent group equation is not the whole story. After we solve, we are plotting expectation, we are plotting the absolute value square of the distribution, not the function itself, and then we find some observables. This is already done in results sections, and in some sense method section just accompanies results and explains how they were obtained. Are there questions to the author, to Fatima, or more suggestions to this work? If no, let's move to the longest piece of today, to the draft of thesis by Kevin. Other volunteers to give comments. Fatima, would you like to share some comments, or just focus attention on the comments that you already did?
I'm good.
Yeah, good. Okay.
Yeah.
Okay, because I see a lot of comments. Aaron, would you like?
I have written.
Huh? Pardon?
So I have written on this document. So
yes.
You can see
yes, but bringing attention is generally a good thing. If you want to, you may just mention what is most important thing.
It's okay. I'm good.
It's okay. Okay, good. Aaron, would you like to bring attention of Kevin to any of the aspects?
I think the most, or the thing that you would get asked about if you're presenting this would be what's the connection between the relaxation rates that you compute and the thermoelectric efficiency.
Uh-huh. Which page should I navigate to?
Well, I guess I wrote it in the conclusions.
Okay.
So I think that would be a natural place to relate the findings to thermoelectric efficiencies. But from reading through, I didn't see, maybe it's in there, and I didn't see it.
Oh.
Because it's mentioned a lot that the relaxation rates are important, but there's no explicit mention of how it relates to the efficiency or how it would be expected to help benefit the efficiency.
Okay. Okay. I want to advocate for Kevin. So this question of connection between our standard approach to modeling photo-induced charge transfer and thermally induced charge transfer is the biggest challenge. The reformulating our standard approach for description of thermoelectric materials is a big thing, and finding this connection is not trivial. So, to my understanding, Kevin is doing first steps on this road, because some of the fundamental processes are similar. Due to thermal fluctuations, the charges are migrating between orbitals localized in different spatial vicinities. But making detailed connection of this of these two pictures is not trivial and maybe not possible within this quick work. So if Kevin will be trying to address a question of Aaron, one can put it like it's standard practice for scientists to admit that only one thing can be done at a time. We have a very ambitious goals, and we made maybe 10% of our original plan. So making it's definitely one can feel that there is a connection between observables for photovoltaic setup and thermoelectric setup, but literal connection between them is yet an open question. And if this will be formulated this way, it will be fitting whatever is required for thesis, and it will be respected approach for a publication. Like if one wants to continue further, this thing needs to be explored more. Do you buy this argument, or you think it is insufficient?
I think the argument makes sense. But then maybe just to beef it up a little bit more, maybe just mention a possible like update to the methodology or a possible future direction. Because that would be something that some committee member will probably have. But it's a standard committee question, I would think.
Yes.
Like what's a possible?
Yes. And I do see. Thank you, Aaron. And I do see entry points for the comments as you suggest. So in yes. So Kevin is telling in the paragraph before figure 15, he is speaking about the superposition of orbitals. So this will be an ideal place to make connection to thermo or additional connection to thermoelectrics, because in our standard approach to photovoltaic setup, we consider initial condition as pair of orbitals originally occupied and originally unoccupied. Promotion of electron from one orbital to another orbital, and this is an approximation, but it does give reasonable results for practical aspects, for mid-range and wide gap semiconductors. For thermoelectrics, this approximation may not be as good. For thermoelectrics, one may need to start the initial condition through exciting multiple originally occupied orbitals into multiple originally unoccupied orbitals to mimic thermal Fermi distribution. So when multiple orbitals get the change in their occupations by small number. Does it make sense?
So are you talking about like an exciton initial condition? Or just a thermally populated?
Thermally populating. And thermally populating at initial time, and then assuming that system is suddenly cooled down, and then the distribution of occupations will return to the 0 Kelvin or lower temperature. So by shuttling the I'll bring another version where I can do written annotations. The kind of annotations. Okay, maybe here. No, it doesn't cooperate here. I'll quickly bring something where one can okay, just at the bottom of Yulun's work. Yes. So if we do have the energy and Fermi energy at 0 Kelvin, it will be standard occupation. And if we will explore the occupations at elevated temperatures, they will be more continuous. So by shuttling between these two cases, the occupations of HOMO and LUMO will transfer between different level of occupations, and it will correspond to spatial migration of charge forward and backward. So if one would want to literally model thermoelectric, this would be the path to go. But on this path, there are some additional challenges that are not do not seem practical to solve in a brief master thesis approach. Do you buy this argument? Or do you see any glowing?
I guess someone who's familiar with VASP, they might ask, for someone who's familiar with VASP, they might ask that VASP naturally accounts for like that smearing.
Yes, but VASP is not automatically describes transition between electronic configurations with different value of the smearing. And VASP doesn't naturally describe the amount, the measure of charge transfer that happens upon change of the smearing. So it looks like a doable direction of research, and the challenges are not drastically different, but it would take longer than a year research. It's like couple 2-3 years project to make some changes in the codes and test it on different systems. So it's a good doctoral project to address these questions that you are posing.
Okay.
Okay. Would you like to focus the attention on more aspects? I can bring the this electronic document back.
I think that was my major comment.
Okay, that's fine. Yeah. I think everything is already shared electronically, so Kevin will be able to read all written comments. We are just discussing something that is worth of discussing and verbally focusing. Yulun, do you have any suggestions to Kevin's work? I think your microphone is muted. Pardon?
Okay, so I guess my biggest concern is about figures.
Okay. Which figure? Which figure should I go to?
Right now, I'm talking about in general. So basically, I guess all figures should have its own figure captions, which should stand by their own. So right now, without reading the manuscript, I don't know what the figure is trying to express. This is my comment. And I guess also some figures are not necessary, I guess. For example, figure 1. What's the point of showing figure 1?
Okay, let me bring it up. Yes, I don't think it is very harmful, but there is no big. I agree that it is not critically needed. If one wants to remove it the overall narration will not suffer. Yeah. So Kevin may consider if the only thing, because it is already a short time before submission the thesis, if deleting a specific figure, then one needs to renumber the figures. But I think it can be done. It's like 15 minutes to renumber all figures. What else would you suggest him to focus at?
And also figure 4.
Okay, I'll bring it up. Okay.
So this is periodic structure, right?
Yes.
Then why a couple sentences before figure 4, he mentions the length is about 110 angstroms. What's the meaning of length here? It's just the size of a unit cell?
Yes, you're absolutely correct.
Okay. And also equation 2 and equation 3, which is very confusing. I don't really understand these two equations.
Okay. So, what are the constructive suggestions to these equations if Kevin decides to keep them? Explain in much details each symbol. Let me explain my vision, which may or may not be agreeing with Kevin's vision. The balancing of charge and the difference between oxidation state of the original host atom and contributed dopant atom later on describes whether selected dopant will serve as N-doping or P-doping. And the equations 2 and 3 are ramping for understanding of the figure 5. In some sense, equations 2 and 3 are more detailed than figure 5, but they, if explained carefully, they should look as as a unified description. That okay. But if you see some constructive suggestions, which practical steps Kevin can do in order to improve these equations, maybe provide more detailed explanation of each symbol, please communicate it to him in writing or by telling now or by sending an email. I believe he will appreciate it.
Okay. Next is figure 5. So what's the difference between panel C and the rightmost panel?
Right, it's figure 6 and where's just a second. Yes, figure 5. Okay, please repeat the question. I need it.
What's the difference between panel C and the panel at the rightmost corner?
I will take role of advocating what Kevin composed. So the way how this figure is done is can be improved. The panel D must include schematic diagram of electronic structure for the co-doped model. Right now, the space the void, the gap between P and N doped materials is exaggerated and used at too high level. So the arrow that shows electron migration goes across the free space. If I will be doing this figure, I would remove this void and jam this sodium doped and iodine doped in D panel together. There is also a little thing that I would improve. It doesn't seem critical to me, but I would improve. In the ground state, the P and N doped materials would equilibrate charge so that the top of the valence band of the sodium doped will be occupied and bottom of the iodine doped conduction band will be unoccupied. And only upon photoexcitation, the arrow that Kevin is indicating by E minus and arrow would happen. So these details would be great to add, and I think it will be less confusing. But again, I do not know if it is possible to do in the given time. Personally, you are aware of the original work by Jinchao Chen, who was trying to make a figure like this. And this work is inspired by the paper by Jinchao. So his version of similar figure could be used as the template and the source. So if you have some constructive comments based on the comparison between this and that implementation of this PN junction, please advise to Kevin.
Okay. And also figure 6.
Okay.
So what's the meaning of a vertical line?
So I do believe that let me bring back the previous figure that we discussed. So if we compare the panel A and panel D, then the gap in the panel D, absolute gap in panel D, will be shorter than in panel A, because there are additional orbitals that are contributed inside the original gap. There is at least one more orbital at the bottom of the conduction band due to iodine doped, and there is additional orbital at the top of the valence band due to sodium doping. If we want to check if the schematic diagram of figure 5 is correct in computations, we may plot density of states of doped and undoped model one above each other and check whether the peaks in these models are similar or different. So if we look onto the panel A and we see that there is no orbitals, no states, no peaks on the dashed lines inside the gap. If we look on the panel B for the co-doped nanowire, we see that the dashed lines come through the center of additional peaks, A prime lowercase and A lowercase. So by analyzing this density of states, one can make hypothetical conclusion that the peak in the valence band B lowercase prime and B uppercase prime approximately correspond to the same orbital that corresponds to the host, to the telluride orbitals of this semiconductor, while the peak A lowercase prime is contributed by the sodium specific orbitals. Same for the conduction band. The peaks B lowercase and B uppercase correspond to intrinsic host orbitals localized on the lead, while the peak A lowercase is present only in the co-doped model and is localized on the iodine orbitals. So in some sense, figure 6 is computational proof of the schematic diagram in the figure 5.
Okay.
Okay. Okay. Where should we go now?
So I guess just below figure 6, there are a couple of standards. So he said the band gap has slightly decreased to 0.9 electrovolts. And these two changes indicate a drastic increase in the nanowire's conductivity. I don't understand it.
I disagree with how it is formulated, but I see logic behind it. So instead of conductivity, I would put ability to participate in the charge transfer events. This would be more adequate. I understand where this wording comes from, because if we make the gap smaller, then the conductivity of material increases. But here, indeed, due to doping, conductivity will increase, but not so drastically. And conductivity is not our main goal in this project. The goal is charge separation, formation of charge separated states, which is the prerequisite for generating of voltage and current later. So conductivity is not our goal in this project. Thank you for catching this.
Next, figure 7. Because here my question is why the spectrum looks so different, considering the density of states is basically identical.
I accept your question. It is very legitimate, and I believe Kevin has some explanation of this difference. So I'm going to bring another version of the same figure, because I was recently going through it. So I suggest if one can use, one can place these panels one under each other in the same range of energies, and then specifically describe each peak or each range. So hypothetically, again, it is too many if statements, but hypothetically, the feature it's hard. I'll go back to previous figure. I'll go back to previous figure. It will be more clear to explain. So the optical transition in the panel A from the feature B prime uppercase to B uppercase is expected to be bright because B prime is delocalized over all atoms, all ions that serve as oxidizing agent, over all telluride ions. Uppercase B is delocalized over all reducing host atoms, over all lead atoms. So the orbit, this HOMO and LUMO in undoped, will cover the whole space. They will have big overlap, and they will provide noticeable oscillator strengths. If we go to a little bit red-shifted transition in the co-doped system, it will be the lowest possible transition will be formally originating from lowercase a prime to lowercase a. These two peaks, these two orbitals are localized only in the vicinity of the dopants. A prime is localized on the around sodium ions. A without prime is localized around iodine atoms. If spatial distribution of orbitals doesn't have overlap, if they are localized in different space regions, then it forbids optical transitions. So this transition will be dark. And through this analysis, the lowest transition in the co-doped nanowire will have some excitations from HOMO to LUMO at low energy, but the brightness, the oscillator strengths of this transition will be dark because it is contributed by charge transfer excitations, and charge transfer excitons are always dark. Okay.
Also, it seems to me the entire paragraph for panel 7, no, figure 7, should be rewriting because there are lots of errors. For example, just read the last sentence of this paragraph. It seems to me it just does not understand the meaning of dark.
I understand, and your comment is legitimate. One needs to, yes, rewriting this sentence would be helpful. And if any of the group members do have suggestions, I think Kevin would appreciate. Yes, maybe completely erase it and rewrite. We do not have time to go over these tiny details, but one needs to dissect each part of the sentence and rewrite it, yes.
and figure 8.
Mm-hmm.
I guess. So go to the last sentence describing this figure. So he says bond contraction. So what's the connection between bond contraction and this figure?
Okay, I understand the direction of thought of Kevin, but without previous history, it's not possible to understand and reconstruct. As it is written, it gives very false interpretation. The original discussion that we had with Kevin was that the displacement of ions moves system on the potential energy curve, and this change in the energy along the potential energy surface is responsible for this, like we are going to different point of energy landscape which may open or close the gap. Definitely there is a correlation between measure of elongation for a specific bond and amount of energy that the gap is opening or closing. But making this conversion from electron volt units to inverse centimeter units is absolutely false analogy. This last sentence just simply converts the amount of change in energy into the spectroscopic units of inverse centimeters. This is not a correct implementation. This sentence is a very good candidate for complete erasing. Yeah, many thanks for being careful and catching it.
Yeah. Also, first sentence of figure 9. What he's talking about? What's the meaning of the conclusion?
This is not acceptable style of writing, and I hope that Kevin is listening and this will be recorded. So the I would, if I would be completely taking responsibility of this work, I would of course do much longer figure captions. The main trend and observation in the figure 9 that rates of transitions between orbitals increase if we put system on a thermostat with larger temperature. This is objective observation. Possible interpretation and hidden correlations is that at higher temperature, the amplitude of fluctuations increases, and a lot of orbitals temporarily experience closure of the gaps and subgaps. And this temporarily closure of gaps and subgaps, or crossing of the energies of orbitals, could be a mechanism to speed up the transitions. So there are two shoulders, two wings for larger intensity of non-adiabatic transitions. First, that larger amplitude of nuclear motion gives larger violation of the orthogonality. The orbitals are over orbitals explored at nearby steps of the trajectory overlap at larger extent. This is one mechanism. And another mechanism, that the subgap that particle, that electron needs to travel in energy space from one orbital to another one, becomes smaller, because as time goes by, these fluctuations close the subgap, maybe not for the whole time, but frequently experience crossing. And I may interpret the direction of thought of Kevin that he wanted to highlight the second opportunity, that temperature-induced fluctuations of orbitals shown in previous figure contribute to enhancement of relaxation rates.
Exactly.
Okay.
The next paragraph refers to this. What's the meaning of an orbital outlier?
Okay. I think I have an idea what Kevin was trying to say. It looks like interpretation of figure 9. At lower temperature, and not only in this computational setup, but in many other projects that we did in the group, the non-adiabatic transitions, the Redfield tensor, shows largest transitions very close to the main diagonal, and everywhere along main diagonal except HOMO to LUMO transition, because HOMO to LUMO has a gap. As far as the temperature increases, this symmetric arrangement fails. First, the transitions for orbitals that are not nearest neighbors along the main diagonal become substantial. And second, direct non-radiative recombination from HOMO and LUMO become noticeable. Okay, at least we agree with it, and maybe Kevin will be able to adjust.
Next paragraph.
Okay.
In the middle, he said, since sodium has 1 extra electrons, all the occupied orbitals would be centered around these dopents. What's the connection? Why?
Okay. I'm not fresh enough to give detailed analysis of this sentence, but it sounds as reference to schematic diagram in figure 5, equations 2 and 3, and numerical data in figure 6 in density of states. So I'm going to scroll there to be more illustrative. So because of the specific electronic structure of the regions doped by sodium, the orbitals contributed by sodium replacement dopant, by sodium replacing telluride, have energy at the top of the valence band, and physically are the charge distributions are localized around sodium ions. So I think it was an attempt to communicate this idea. The best way to communicate this idea in this context would be, I think he's showing the HOMO. So this idea is illustrated to some extent.
Okay. Next paragraph. In the middle, there is sentence starting with however. It doesn't make sense at all. And also, is there some curious trend? I also do not understand.
So I would suggest to completely remove this due to log scale of time. This is completely irrelevant. The word later is also irrelevant here, but I believe it means like later on the table. I would put here higher values. So the higher the temperature, the earlier the relaxation. Okay.
And the following sentence, we talk about magnitude of energy difference, which is very confusing.
Yeah, I do not see interpretation, and if Kevin doesn't explain it in a better way, I would suggest just to remove the sentence. Yep. Maybe
yeah, that's all.
Yes.
I have no further comments. That's all.
Okay. Yeah. Many thanks. It's very valuable, and I think it will prevent the work and the author from difficulties with reviewers and committee. So let me quickly go over my comments, and then I think we are already over time. We will finish soon. So I don't know if it is good or bad, but I'm starting reading from conclusions. Well, it is not experiment, it is numerical experiment, or first principles numerical experiment. I would check measure of charge transfer. So rate is too specific. Here in the last sentence of this paragraph, I'm not sure which transition is being focused about. Again, this is a synonym, like numerical experiment, atomistic computation. This is not, being more specific. We study specific nanostructure. We are not telling here about general trend. It is one applied problem. At the end of second paragraph, I think Kevin is speaking about choice of initial excited orbitals. Instead of theory, I would say material science. It is a little less ambitious but more practical. Starting from initial conditions. So it is, I would highlight it if it is applicable. Instead of phenomenon, just tell explicitly initial photoexcitation or general initial excitation. I saw the comment by Fatima that it is not quite common to use figures in the conclusions, but to my understanding, this figure was added at the very late stage of writing. Maybe it could be placed in the introduction, but then the whole introduction needs to be rearranged. And this figure relates to direction of future works. This figure is not, this model hasn't been computed in this thesis, and it would be maybe deceptive to put it earlier. So maybe some good words about Owen's work. One is getting findings, observations, trends from this numerical experiment, and it is applicable only to certain class of nanostructures. This is not theory of the whole world, and if you show that it is ranges of applicability, it is a good thing. There is a interesting, it's kind of trivial finding, but since it is educational process, since it is master thesis, it would be very relevant to highlight that this work confirms that providing the dopings of P and N doping enhances ability of material to perform charge transfer. And it is right now, although through the collective editing, I do see there were a lot of help and to Kevin to avoid errors or hard places in the writing. The main shortage, main problem that committee will tell, there are no references. I would pose it as a goal number one, to put as much references as possible, and this is best done with EndNote. If you never used EndNote before and there is a difficulty challenge with license, the trial license is available for 30 days, and probably within 30 days the whole story with this thesis will be successfully completed, so it is a good decision. For figures, I think Yulun provided and Aaron and Fatima provided really great analysis of figures and text. Personally, I would rearrange absorption spectra one under another to help analysis, and maybe label all peaks to speak about them. For this density of states, only range inside this black box makes sense. We are not making excitations higher than like 1 electron volt above the band edge. Here I'm repeating comments or old comments about the methods, and they're very basic. So fix subscripts for like, or superscripts. For consham it should be a superscript, I should be subscript. The equation 11, it is Redfield tensor letter R that drives the relaxation, not letter M. Letter M autocorrelation function is connected to letter R through Fourier transform. So I'm suggesting to remove letter M and use letter R in equation 11. And another thing I feel picky and complaining, the use of symbols for expectation value of energy. So, and this seems to be easy to fix. Please meditate and focus on it. Right now, I do see 3 symbols for the observable that looks the same or almost the same. So uppercase E with subscript EH, upper script E with the word electron, and delta E Greek letter. Are they the same or they differ by conversion factors? So please clarify this this aspect. Okay, I'm done with my comments, and let me ask if anyone has any suggestions or comments before we disconnect and depart. If no, I suggest all reviewers share the feedback with authors. So for Kevin, the comments of Fatima and Aaron are online along the link. The comments by Yulun were verbally expressed, and I will try my best so this recording will be processed and shared. And my brief comments, I'll send them. Okay. So if you will have time during the day tomorrow, please try to submit abstracts to Pacificam. There could be, since it is in the December and during the summer, there will be answers from grant agencies. There is a chance that there will be opportunity for several group members to travel to Hawaii. This conference happens once per 5 years, and last time I think there was a chance to bring like four group members to this conference. like Stephanie, John, Wendy, and Adam did travel and present there. Okay, I do not have any messages to distribute among everyone. I suggest we complete the meeting and disconnect, and I will stop the recording and stay here just in case there are more questions in private or not so important for the whole group. Thank you much for helping each other. I think it is a great great help and great teamwork for this collective editing. Okay. I'm going off record.